Hello, my name is Dr. Volodymyr Krasnoholovets. I am a senior scientist at the Institute of Physics, National Academy of Sciences of Ukraine, and a visiting professor at the Institute for Basic Research, Florida, US. For centuries, we've harnessed chemical reactions to transform our world from the simplest fire to the most sophisticated pharmaceuticals. But what if we could conduct these reactions with a precision and speed we never thought possible? What if there's a hidden realm or energy and field that is influencing these molecular dances? In the realm of the ultra-small, a revolutionary theory proposes the existence of inerton fields, a concept I formulated and proposed back in 1984. These fields hold the key to unlocking unprecedented control over the very building blocks of our universe. Imagine a world where chemical reactions, the bedrock of countless industries, could be accelerated to unimaginable speeds. Imagine pharmaceuticals synthesized in minutes, not months, or materials with properties exceeding our wildest dreams. This isn't science fiction. It's the tantalizing promise offered by inerton field theory. The inerton field are an energy source that is available to harness any time they are required on a 24-hour, 7 days a week basis. Unlike most renewable energy systems that depend on weather conditions and sunshine levels, etc., and are vulnerable to physical destruction. In many chemical processes, a catalyst along a source of heating and cooling must be applied for the initiation of the chemical reaction and control of the reaction rate. This increases the capital cost of the plant for heating and cooling systems, and also the energy usage associated with them. We have already developed systems that use inertons to make biodiesel from vegetable oils in minutes rather than days, and without the need for heating and cooling requirements of conventional biodiesel processing requires. Join me as we embark on a journey into the heart of this groundbreaking theory, exploring its potential to redefine the boundaries of chemistry. Let's delve into the core of how chemical reactions occur. Molecules, those tiny building blocks of matter, are in constant motion, colliding with each other, but not all collisions result in a reaction. For a reaction to happen, molecules need enough energy to overcome an energy barrier, like a hill they need to climb. Now imagine if we could subtly reshape the landscape of that hill, smoothing the path and making it easier for molecules to reach the peak and react. That's precisely what manipulating inerton fields could achieve. By influencing these fields, we could effectively reduce the energy required for reactions to occur, leading to significantly faster reaction rates. It's like trying to roll a boulder uphill. It's a slow and arduous process. What if we could somehow reduce the incline of that hill? The boulder would roll up much more easily and quickly, saving you energy and a lot of stress. That's the power of manipulating the inerton field. We are essentially manipulating the energy landscape of the chemical reactions, making it easier and faster for them to occur, and of course, reducing the need for expensive external energy into the system to initiate and control the reactions. This ability to fine-tune reaction kinetics using inertons has profound implications. It could revolutionize industrial processes, making them faster, more efficient, and less energy intensive. The possibilities are truly limitless. Imagine a crowded room full of people trying to find their dance partners. The faster they move through the crowd, the quicker they find their dance partners and start dancing. Now think of molecules as those dancers, and their reactions as the dance itself. In the world of chemistry, diffusion, the movement of molecules from an area of high concentration to low concentration, plays a critical role in how quickly reactions occur. Inerton fields, like an invisible hand, can influence the rate at which these molecules react. By subtly adjusting these fields, we can effectively speed up the movement of molecules, allowing them to find their reaction partners more quickly. Imagine a crowded dance floor suddenly becoming less congested, allowing dancers to move freely and find their partners with ease. This accelerated diffusion has the potential to significantly speed up a wide range of chemical processes, particularly those limited by how fast molecules can mix and interact with other molecules. From the synthesis of new materials to the development of more efficient catalysts, the implications are far-reaching. Every chemical reaction faces an energy hurdle it needs to overcome before it can proceed. Pause 2 seconds, this is called the activation energy. Think of it as the initial push required to get a reaction going. The higher the activation energy, the slower the reaction, like trying to push a heavy object uphill. Inerton fields offer an intriguing possibility: the ability to lower this activation energy barrier. By subtly altering the energy landscape of a reaction, we could effectively reduce the amount of push needed to get it going. Imagine smoothing out that uphill climb, making it easier to push the object to the top. This ability to lower activation energies could revolutionize countless industrial processes. It allows reactions to occur at lower temperatures, reducing energy consumption and making them more environmentally friendly. It could also open doors to synthesizing new materials that were previously impossible to create due to high activation energy barriers. For a chemical reaction to occur, molecules need to collide with each other. But unfortunately, not all collisions are created equal. Only those with enough energy and the right orientation will lead to a successful reaction. It's like trying to fit two puzzle pieces together. They need to align perfectly for a connection to be made. Inerton fields act as an invisible force, subtly influencing the movement and orientation of molecules. By manipulating these fields, we can increase the frequency of effective collisions, those more likely to lead to a reaction. Imagine a cosmic dance where the dancers are guided into perfect alignment for a seamless performance. This increased collision frequency therefore can have a dramatic impact on reaction rates. By maximizing the number of successful collisions, we can enhance the efficiency and speed of a wide range of chemical processes, from the synthesis of pharmaceuticals to the production of new materials. Imagine a mountain pass connecting two valleys. To travel from one valley to the other, you need to cross this pass, which represents a higher energy state. Similarly, in a chemical reaction, molecules often pass through a high energy transition state before forming the final products. The stability of this transition state is crucial. The more the reactions are easier, it will be for the reaction to proceed, like having a well-maintained path through the mountain pass. Inerton fields offer the potential to influence the stability of these transition states. By subtly adjusting these fields, we could stabilize these high-energy intermediates, making it easier for the reaction to proceed and forming products more quickly. It's akin to paving the mountain pass, making the journey smoother and faster. This ability to manipulate transition states could have profound implications for chemical synthesis, allowing us to create new molecules and materials with greater precision and efficiency. Imagine a line of dominoes perfectly arranged. Flicking the first domino sets off a chain reaction, transferring energy efficiently down the line. Similarly, in some chemical reactions, energy can be transferred between molecules in a highly efficient process called resonant energy transfer. Inerton fields, like a conductor's baton, could influence this energy flow. By subtly tuning these fields, we could enhance the efficiency of resonant energy transfer, making reactions proceed more rapidly. It's like optimizing the spacing between dominoes for a faster, more impactful chain reaction. This enhanced energy transfer could have significant implications for various fields. In solar energy, for instance, it could lead to more efficient capture and transfer of sunlight, paving the way for more powerful solar cells. The possibilities are truly exciting. Imagine a game of hot potato where players quickly pass the hot potato from one person to another. Similarly, many chemical reactions involve the transfer of electrons between molecules. The faster and more efficiently these electrons are transferred, the faster the reaction proceeds. Inerton fields could act as a catalyst for electron transfer. By subtly influencing the energy levels of molecules, we could facilitate faster and more efficient electron exchange. It's like greasing the hot potato, making it easier and faster to pass from one player to the next. This enhanced electron transfer could have a profound impact on various chemical processes, particularly those involving oxidation and reduction reactions, which are fundamental to a wide range of industrial and biological processes. Imagine a guitar string vibrating at a specific frequency, producing a particular note. Similarly, molecules vibrate at specific frequencies, and these vibrations play a crucial role in chemical reactions. By altering the vibrational states of molecules, we can influence their reactivity. Inerton fields offer the potential to act as a tuning fork for molecular vibrations. By subtly manipulating these fields, we could excite or dampen specific vibrational modes, effectively tuning the reactivity of molecules. It's akin to adjusting the tension of a guitar string to produce a desired note. This ability to manipulate molecular vibrations could open up exciting possibilities in chemical synthesis. It could allow us to selectively activate certain molecules or functional groups, leading to more precise and controlled reactions. Imagine a solvent as a dance floor and molecules as dancers. The nature of the dance floor influences how easily and freely the dancers can move. Similarly, the solvent environment plays a crucial role in chemical reactions, affecting how molecules interact and react. Inerton fields, like an invisible choreographer, could influence the properties of the solvent itself. By subtly adjusting these fields, we could alter solvent viscosity, polarity, and other factors that influence reaction rates. It's like changing the texture of the dance floor, making it more conducive to certain types of dance moves. This ability to fine-tune solvent dynamics could have significant implications for various chemical processes. It could lead to more efficient reactions, improve selectivity, and even enable reactions that were previously impossible in certain solvents. Imagine a crowded room full of people, and you want to get the attention of just one person. You could call their name, selectively exciting their auditory senses. Similarly, in a mixture of molecules, we might want to selectively excite specific molecules to undergo a particular reaction. Inerton fields could allow us to do just that. By tuning these fields to resonate with specific molecular vibrations or energy levels, we could selectively excite certain molecules while leaving others unaffected. It's like having a molecular whisper that only the targeted molecules can hear. This selective excitation could be a game changer in areas like drug delivery. We could potentially activate drugs only at their target sites, reducing side effects and enhancing efficacy. Catalysts are like matchmakers in the world of chemistry, facilitating reactions without being consumed themselves. They do this by providing an alternative reaction pathway with a lower activation energy. Inerton fields offer the potential to enhance the effectiveness of catalysts. Imagine a catalyst as a busy bee, flitting from flower to flower, facilitating pollination. Inerton fields, like a gentle breeze, could guide the bee towards the flowers more efficiently, increasing the rate of pollination. Similarly, by subtly influencing the interactions between catalysts and reactant molecules, inerton fields could enhance catalytic activity, leading to faster and more efficient reactions. This enhanced catalytic activity could have significant implications for various industrial processes, making them more sustainable and cost-effective. It could also pave the way for developing new catalysts with unprecedented efficiency and selectivity. Imagine a staircase where each step represents a different energy level for an electron within a molecule. The energy difference between these steps determines how easily electrons can transition between them, influencing the molecule's reactivity. Inerton fields could act as an elevator for these energy levels. By subtly adjusting these fields, we could modify the spacing between energy levels, making it easier or harder for electrons to transition. It's like adding or removing steps from the staircase, altering the ease with which electrons can move up or down. This ability to fine-tune energy levels could have a profound impact on various chemical processes. It could allow us to control the absorption and emission of light by molecules, leading to advances in areas like optoelectronics and solar energy. Imagine a relay race where the overall speed depends on how quickly the baton is passed between runners. Similarly, many chemical reactions involve the formation of intermediate species that act as stepping stones to the final product. The faster these intermediates are formed, the faster the overall reaction. Inerton fields could act as a coach for these intermediate species. By subtly influencing the energy landscape of the reaction, we could facilitate the rapid formation of these crucial intermediates. It's like training the runners to pass the baton more efficiently, leading to a faster overall race time. This accelerated intermediate formation could have significant implications for complex chemical synthesis. It could allow us to synthesize complex molecules more efficiently and with greater control over the reaction pathway. Imagine navigating a maze where multiple paths lead to the exit, but some are shorter and more efficient than others. Similarly, chemical reactions can proceed through different pathways, each with its own energy barriers and intermediates. Inerton fields could act as a GPS for chemical reactions. By subtly influencing the energy landscape, we could guide the reaction along a more favorable pathway, bypassing high energy barriers and accelerating the overall process. It's like choosing the most efficient route through the maze, avoiding dead ends and reaching the destination faster. This ability to optimize reaction pathways could be a game changer in chemical synthesis. It could allow us to create desired products with greater selectivity and efficiency, minimizing waste and reducing the environmental impact of chemical manufacturing. Imagine a greenhouse where temperature, humidity, and light are carefully controlled to create the optimal environment for plant growth. Similarly, the environment in which a chemical reaction occurs can significantly impact its rate and outcome. Inerton fields could act as an invisible gardener for chemical reactions. By subtly influencing the reaction environment, we could create more favorable conditions for the desired reaction to occur. It's like adjusting the temperature, humidity, and light in the greenhouse to optimize plant growth. This ability to fine-tune the reaction environment could lead to more efficient and selective chemical processes. It could also enable reactions that were previously difficult or impossible to carry out under conventional conditions. Imagine a conductor leading an orchestra, carefully controlling the tempo, volume, and dynamics of the music. Similarly, understanding and controlling the mechanism of a chemical reaction is crucial for optimizing its outcome. The reaction mechanism outlines the step-by-step process by which reactants are converted into products. Inerton fields could act as a molecular conductor, allowing us to fine-tune the reaction mechanism to achieve desired outcomes. By subtly influencing the energy landscape of the reaction, we could favor certain mechanistic pathways over others, controlling the speed and selectivity of the reaction. It's like the conductor adjusting the orchestra's performance to achieve a specific musical effect. This ability to orchestrate reaction mechanisms could revolutionize chemical synthesis. Imagine trying to organize a messy room. The more objects you have, the more difficult it is to arrange them in an orderly fashion. Similarly, in chemical reactions, entropy, a measure of disorder, can create barriers. Reactions often require molecules to come together in a specific orientation, which can be challenging due to their natural tendency to spread out. Inerton fields could act as an invisible organizer in the world of chemistry. By subtly influencing the interactions between molecules, we could reduce entropic barriers making it easier for molecules to adopt the necessary orientations for a reaction to occur. It's like having an invisible hand guiding the objects in the messy room into an organized state. This ability to overcome entropic barriers could significantly impact reactions that are normally slow due to the need for molecules to adopt specific orientations. Imagine a crowded train station where people are trying to board a train. The more accessible the train doors, the faster people can board. Similarly, in chemical reactions, the accessibility of reactive sites on molecules plays a crucial role in determining reaction rates. Inerton fields could act as door openers for chemical reactions. By subtly influencing the conformation of molecules, we could increase the accessibility of reactive sites, making it easier for other molecules to interact and react. It's like widening the train doors to allow for faster boarding. This increased accessibility could significantly impact reactions involving large, complex molecules, where reactive sites might be hidden or difficult to access. It could lead to faster reaction rates and new possibilities in areas like drug design and material science. Imagine trying to stack a tower of blocks. The more precisely the blocks are aligned, the more stable and taller the tower can be. Similarly, in some chemical reactions, the alignment of molecules plays a crucial role in determining the reaction's outcome. Inerton fields could act as an invisible architect in the world of chemistry. By subtly influencing the orientation of molecules, we could enhance their alignment, leading to more efficient and selective reactions. It's like having an invisible guide ensuring that each block is perfectly placed, resulting in a taller and more stable tower. This ability to control molecular alignment could be particularly important in reactions involving chiral molecules, which exist in two mirror image forms. By precisely aligning these molecules, we could selectively synthesize one chiral form over the other, which is crucial in areas like drug development. Imagine a bouncing ball. With each bounce, some energy is lost as heat due to friction and air resistance. Similarly, in chemical reactions, some energy is inevitably lost as heat, reducing the overall efficiency of the process. Inerton fields could act as energy conservationists in the world of chemistry. By subtly influencing the energy flow within a reaction, we could minimize energy dissipation as heat, making more energy available to drive the reaction forward. It's like reducing the energy lost with each bounce of the ball, allowing it to bounce higher and for a longer time. This ability to conserve energy could have significant implications for various chemical processes. It could lead to more efficient reactions, reduce energy consumption, and minimize the environmental impact of chemical manufacturing. As we've explored, the potential of inerton fields to revolutionize chemistry is vast and awe-inspiring. From speeding up reactions to unprecedented levels to unlocking new synthetic pathways, the inerton energy fields holds the key to transforming countless industries and addressing some of humanity's most pressing challenges. However, the journey from what was a theoretical concept to now real practical application was paved with meticulous research and experimentation. The future of chemistry is a symphony of possibilities, and inerton fields might just hold the conductor's baton. By unraveling the mysteries of these invisible fields, we unlock a future where the building blocks of our universe can be orchestrated with unprecedented precision and finesse, leading to a brighter and more sustainable future for all.